Hello and welcome to this lecture. So in the previous lecture we saw one method of integration which was very important. It was integration by substitution. You had to look at the integrand and sort of identify the some subpart of a function and its derivative both being there or something like that, and then basically you substitute some complicated looking part inside the integral with a variable, and then that gives you some way of doing the integration, right? So otherwise the basic problem is this product rule, quotient rule and all doesn't exist directly for integration. So you have to do these clever tricks to come up with methods, okay. One such very interesting and important method is something called integration by parts, okay. So that's the method we're going to see in this lecture. So let's get started. So the basic idea is the following. I've given you the sort of the theorem and the proof. It's easy to sort of see. Supposing you have a function capital F of x, and this function has to have this strange sort of form. What is this form? It should be u of x times v of x minus the antiderivative. You remember this a represents the antiderivative, right? Antiderivative of u prime v of x, okay. Strange, I know it's strange, but then what happens to this kind of a form is the following. If you differentiate it, notice what happens. You take this u of x, v of x, uv, if you forget the of x, uv minus a u prime v of x, right. So minus a u prime v, uv minus a u prime v. If you take the derivative of that, something very nice happens. This is what happens. What's the derivative of u of x, v of x? U of x, v prime of x plus u prime of x, v of x, isn't it? This is just the product rule. And what's the derivative of a u prime v of x? It's the derivative of, the derivative of this is simply u prime of x, v of x. And we have designed it so that this u prime of x, v of x will cancel with this u prime of x, v of x, and you will be left only with this product u of x, v prime of x, okay. So that gives you the integration by parts. So if you have a small f which is the product of a function u of x and the derivative of another function v prime of x, okay, then its antiderivative has this form u of x, v of x minus the antiderivative of u prime v of x, okay. So that is the form of this theorem. This is the by parts idea, okay. I hope you see this. I'm going to show you why this is true. I want the antiderivative of u v prime, okay. You can get the antiderivative of u v prime as u v minus a u prime v, okay. So for this to be executed, the antiderivative of u prime v should be easy, right? You should know the antiderivative of u prime v. So you know the antiderivative of u prime v, you don't know the antiderivative of u v prime. So if you know one of them, you can find the other, okay. So that's what it means, right? So that's how the method works. So let me show you a few examples to illustrate what I mean, okay. So you have to, the example proceeds in this fashion. You have to identify the u and v prime, okay. So in substitution, you have to identify some subfunction and substitute, right? Like that. In parts, you have to identify the u and v prime. So by parts, sort of, you identify u and v prime, and then you find a u prime v, okay. This antiderivative of u prime v should be something easy to find. Find u v prime, like that, okay. So I'll show you some examples. It has some very powerful, nice examples. So here's a product form, x times e power x, okay. I don't know immediately the antiderivative of this. I know the antiderivative of e power x, I know the antiderivative of x separately, but if I multiply them, I don't know the antiderivative immediately. But let's try and see if we can identify u and v prime. What should you identify as u? What should you identify as v prime? Okay. So you can try both, but I'm going to give you the answer directly. You can identify u as x and then v prime as e power x, okay. So it turns out the exponential function should get a preference for getting identified as v prime, okay. So you'll see why. The reason is, if you identify the simpler function as u, the derivative is easier, and in fact it will vanish and things will become better for you. So if v prime of x is x, e power x, v of x is e power x, right? The derivative, the antiderivative of e power x is e power x itself. And what is u prime of x times v of x? It is just e power x itself. So if you had taken the other way around, you will see you won't get something like this, okay. So let me just show that to you, okay. So you have a function x times e power x. I was claiming I will take u to be x and v prime to be e power x. So this gave me v to be e power x itself, and u prime v became 1 times e power x, that is e power x, right. So, this was nice. I can find the antiderivative of u prime v, that will be e power x itself, right. It is easy to do. Suppose I had done the other way around, I identified u as e power x and v prime as x, okay. So, some people may argue that is also okay. So, if you do that, you will get an antiderivative here as x squared by 2, maybe plus c, that is not relevant here, it is just x squared by 2. And what is u prime v? That is e power x times x squared by 2. I have gone in the opposite direction, right. Instead of reducing this x to 1, I have gone to e power x into x squared by 2, and this I do not know, right. I am stuck. So, you notice the difference here. So, you have to pick v prime to be e power x and u to be x, so that you get u prime v to be something for which the antiderivative exists, okay, exists or you can easily find, okay. So, this is the principle, and this is very important, and that worked out very nicely here, okay. So, once you do that, I know u prime v. How do you find a u prime v? That is just e power x itself, right. E power x antiderivative is itself, you are done. So, now we apply the parts rule, okay. So, what is the antiderivative of f? It is uv minus this guy. So, x e power x minus e power x, of course, you can add a plus c, it does not matter what you add. You can check, this is very interesting, right. So, x e power x minus e power x, okay. So, if you take x e power x minus e power x, this is the same as, you know, x minus 1 times e power x, right. So, if you take its derivative, x minus 1 times e power x derivative, it will be x minus 1 times the derivative of e power x plus x minus 1 derivative times e power x, right. So, that is x minus 1 times e power x plus e power x, right. So, derivative of x minus 1 is 1, isn't it. So, it is just e power x, and that if you notice x e power x minus e power x plus e power x, these two things cancel and you have what you want, okay. So, notice how this works. It is very nice that for x e power x, antiderivative is x minus 1 into e power x, okay. Nice little formula that you get through the by parts method, okay. So, you can do a little bit more. Here is a function which is x squared times e power x, okay. What do you do with x squared times e power x? So, here also you can identify a u and v. Since I already know x e power x, I am going to do this little trick of identifying u to be x and v prime to be x e power x. If v prime is x e power x, what is v? V is x e power x minus e power x, right, x minus 1 into e power x, and then u prime into v will simply become x e power x minus 1, okay. So, now I need the antiderivative of x e power x minus e power x, okay. That is very easy, isn't it? Why? How do I get x e power x minus e power x antiderivative? Okay. So, x e power x minus e power x, so this is my u prime v. So, the antiderivative of u prime v is the antiderivative of x e power x minus the antiderivative of e power x. What is the antiderivative of x e power x? Just now we saw x minus 1 into e power x. This is minus just e power x itself. So, you get x minus 2 e power x. Okay. So, that is how it was done very quickly. So, you got x e power x minus 2 e power x. Okay. Now, what is the antiderivative of f? You plug in this u times v minus this guy, and if you do that and simplify, you will get this answer. Okay. X squared e power x minus 2x. It is just u times v minus this guy. Okay. So, you will get this. You can check that out. You will get this. That is the antiderivative. Okay. So, this looks a little bit more complicated. You can pull the e power x out. You see, you get x squared minus 2x plus 2 times e power x. Okay. So, that is some sort of a general rule. If you have a polynomial multiplying e power x, its antiderivative will be another polynomial multiplying e power x. But that polynomial will not be something just like x or x squared. It will be some slightly more complicated polynomial, and it will come from the parts formula. In fact, you can generalize that a little bit more. Okay. So, I hope you saw the power of parts, complicated products for which you do not know the antiderivative directly, you can do with parts. Okay. So, let us go ahead and see a few problems. Here are a few problems for this. It is asking you to evaluate a few definite integrals. The first one is x squared e power minus x. Okay. So, let us maybe show you one or two of these. Okay. So, the first question is x squared e power minus x, right. So, how do you find the antiderivative for this? You can try and do this in multiple ways. So let me show you another method. So, just say we took u to be x squared and v to be e power minus x. Let us say we did that, sorry, v prime to be this. So, then v would be minus e power minus x, okay, and u prime v will be 2x times minus e power minus x, which is minus 2x e power minus x, right. So, I do not know this. So, I need to find the antiderivative of this, right. So, what I will do for that is, okay, here is the trick. So, you can think of this as minus 2, okay. So, let me just write it, it is minus 2 times antiderivative of x e power minus x, isn't it. So, what do I do with this guy? For this you can use parts again. Okay. I need to find the antiderivative of x e power x, x e power minus x. Let me find u to be x and v prime to be e power minus x, okay, and then v will be minus e power minus x, okay, and u prime v is just minus e power minus x, and antiderivative of a u prime v is e power minus x, isn't it. So, this is very easy. So, now antiderivative of x e power minus x is u v, which is minus x e power minus x, right, minus this antiderivative e power minus x, okay. So, which is minus x plus 1 e power minus x. At this juncture it is good to check that this is if you differentiate it you will get x e power minus x, okay. So, there is a minus outside, you can keep it aside, then you have x plus 1 times minus e power minus x, right, plus e power minus x times 1. So, that minus e power minus x and this will cancel and you will end up with, there is a minus and minus that will cancel and you will get x e power minus x, seems to work out. So, this is correct. So, you should check anytime you get an antiderivative, do a differentiation and check that it is correct, it is easy enough to do, right. I think you can check that. So, now I will plug this back in here, now I know the antiderivative. So, I get minus 2 times this, so it is 2 times x plus 1 e power minus x, okay. So, again check, okay, don't be without checking, you can check that this differentiates to that. So, here is a check, 2 times x plus 1 times minus e power minus x plus e power minus x. So, the minus and minus will cancel and you will get minus 2x, okay. So, that works out correct, okay. So, this is a u v prime. So, if you do a x squared e power minus x, that is just u v, which is minus x squared e power minus x minus this guy, which is 2 times x plus 1 e power minus x. So, you can write it very differently if you like, minus x squared plus 2x plus 2 e power minus x, okay. So, that is the antiderivative plus c, you can add a plus c here at the very end, okay. So, you saw how I went ahead and found the antiderivative, and once you find the antiderivative, it is really easy. You can just substitute that back in there, and so integral, I think the question was asking 0 to 5 or something like that, okay, 0 to 5 x squared e power minus x dx, and that is just minus x squared plus 2x plus 2 e power minus x. You know this notation, right? 0 to 5, you put in 5, you put in 2 and you subtract, put in 0 and you subtract, you will get that. What am I going to get for 5? Minus 25 plus 10 plus 2, that is 37, right? 37 e power minus 5 minus, right. So, this is when x is equal to 5 minus when x is 0. So, you will get minus 2 times 1, okay. So, you will get 2 minus 37 e power minus 5 is the answer. So, some number. So, you will get that, you can evaluate this. E is some roughly 2.718, right. So, you will put that in there, you will get some positive value. So, this has to be positive, right. So, you can see x squared times e power minus x, if you plot it, e power minus x is going to fall off like this, x squared is going to go off like this. So, if you multiply these two, you will get something that increases and then decreases, right. So, if you go from 0 to 5, it is all positive all the time, you should get this area, and that area works out to this number, and it needs to be positive, you can check that it is positive, it will work out correctly, okay. So, that is the first definite integral. There are various ways in which people write these steps, right. So, these steps of antiderivative, how I did the antiderivative here, can be written in so many different ways. For instance, here is one way to write this. So some of you might have seen this. People write like this, so you write keep x squared here, and then you take e power minus x inside the d sign. Okay, so this is like a this is a very common sort of way to quickly write this. What do I mean by taking it inside? So this guy is equal to minus, so the derivative of this, right, the derivative of minus e power minus x times dx. Okay, what is the derivative? It's minus everything will go off, you will get e power minus x dx. Okay, so these two are equal. Okay, so this is the way in which you will do it. And then anytime you have something into e power minus x, you can multiply these two guys, minus x squared e power minus x, and evaluate it between 0 to 5, and then do a minus integral 0 to 5, switch these two, right. You put minus e power minus x dx squared. Okay. So this is something that I have learnt in school. So this is how I used to write it. For definite integrals, I used to do this. So you do this, and then you will see if you put 0 will go away, you will get like minus 25 e power minus 5. Okay, and then this will become plus integral 0 to 5 dx squared is 2x dx. Okay, so the 2 will come out this side, and you will have x e power minus x dx. Okay, so this is the same as 2x dx, right. So the derivative of x squared times dx. Okay, and this you know already, right. So now you can repeat the same thing, right. You can repeat the same thing. So how do I do this integral? This is the same as integral 0 to 5 x d minus x, and you will get minus x e power minus x between 0 to 5 minus integral 0 to 5 minus e power minus x dx. This is just another way of writing that the same thing I did, and you will see this will work out as 0 will go away, you will get minus, so it will be minus 5 e power minus 5, and you will have here plus integral 0 to 5 e power minus x dx. And this, at this point, I know the definite integral, so I can write it down as minus plus minus e power minus x between 0 and 5. Okay, and that will end up being minus 5 e power minus 5, and you will put a minus there, so you will get plus 1 minus e power minus 5. So you plug that back in here, you will get the same answer. Okay, so this is another way in which I would like to write parts. So notice this differential notation. We push the function inside the differential notation and sort of replace it like this, and then after that the parts method will work as this is how I learnt it. A to b u dv is uv between a to b minus integral a to b v du. Okay, so this is the way I learnt a parts formula. It's the same as what I used right here as antiderivatives and plugging it back in. You can do it either way, whatever method works for you, but this way you just continue on and finish the problem directly. I'll urge you to substitute back here and then go back and check that you got the same answer as what you got earlier. It should be the same. Okay, so this is a nice way in which to remember the parts formula for definite integral a to b u dv is uv substituted between a and b minus integral a to b v du. So in sort of differential notation, this works out very cleanly. Okay, so the next one is x cube e power x. This is the same as what we did before. You have to repeat it 3 times, pull the e power x inside the differential sign, use the u dv rule, parts rule, keep continuing to do it. You have to do some 4 steps, or you can do the antiderivative way also, the way I mentioned it again and again you can repeat. Okay, so let me do this problem for you, integral 1 to 2 e power root x dx. Okay, so is this going to give us anything interesting? Let's try that. Integral 1 to 2 e power root x dx. Okay, so one can try to visualize these functions. You can plot it on Desmos. I mean, you should definitely try that so that you get a sense of how this works. But in these kind of situations, the first step to always do is a substitution, right? So you're seeing e power root x. This root x is appearing as a small function inside the bigger function. So you should always substitute. So you can put u equals root x. and do the differential formula. So, you get du is 1 by 2 root x dx. So, root x is again u, right. So, 1 by 2 u dx, or this is equivalent to dx being 2u du. Okay. So, this is important. And how do you do the substitution here? If x is 1, u becomes, so this is x equals, so this will become u equals 1 to root 2, right. If x is 2, u is root 2. You put e power, instead of root x you put u, instead of dx you put 2u du. So, notice how by the substitution you got to a form where you can use parts. So, 2 integral 1 to root 2 u e power u du. So, now you can use parts, right. So, of course, you know the antiderivative of this, it is just u minus 1 e power u. You can use that directly, or you can use my wonderful little parts method I showed you, integral 1 to root 2 u d of e power u, and that is u e power u between 1 and root 2 minus integral 1 and root 2 e power u du, and that is just root 2 e power root 2 minus e power u minus e power u between 1 and root 2, right. So, that would be root 2 e power, I am sorry, this is just e power minus e power root 2 minus e. Okay. So, these two will cancel and you will get root 2 minus 1 times e power root 2 as you would have expected directly also. So, there is a 2 multiplying that, you can do that. Okay. So, I just wanted to show you one more way in which I use this u dv type rule very quickly to get it out, and you can check this out. You can pause the video here, stare at it, make sure you understand the steps, or you can use the antiderivative of this directly. So, you may have, so anytime you have an integral with some function appearing inside it, try the substitution, you may get something interesting out of it, right. So, that is a good moral of the story there. Okay. And then this one is also something similar, x e power x squared minus 1, you can make a substitution for this x squared minus 1, right. You put u equals, oh, there is a dz here, this is something wrong, there is a typo here, this should be dx, okay, apologize for that. So, that is dx. So, you can put a substitution u equals x squared minus 1 and you will see it will work out, okay. Try that substitution here for the fourth question, okay. So, the next two are sort of word problems, but they essentially involve some integration and you will see how it works, right. So, a particle is moving with a speed of v of t is t e power minus t meters per second. So, this is just a description of the function which is the speed, how much distance does it travel from 0 seconds to 1 second, okay. So, at 0 second it has got a speed of 0, at 2 seconds it has got a speed of 2 e power minus 2, but then the speed varies, isn't it. So, how do you go from distance traveled to distance traveled from speed? So, you know already that x of, if you do the integral from 0 to 2 v of t dt, this is going to be distance traveled, right. Now, this v of t is given as t e power minus t dt. Now, it just becomes an integration problem, okay. So, I am not going to repeat this integration problem, you have seen how to do this integration earlier. So, you just have to integrate this between 0 to t. Okay. So, let us look at the second problem here. For a capacitor, I of t is given as 2 v prime of t, and I of t itself is going to be e power minus t, it is decaying as e power minus t, and v of t is the voltage across the capacitor. You are assuming v of 0 is 0 and you have to find v of t, okay. So, in this problem you are given I of t, okay. So, let me just change this to, so this problem you are given I of t is 2 v prime of t, right, and the form of I of t is given e power minus t, right, and you have to find v of t. So, in this case v prime of t becomes 1 by 2 e power minus t, right. So, this is the formula. So, how do you go to v from v prime? You have to use the fundamental theorem of calculus and what it means, right. V of t minus v of 0 is integral from 0 to t v prime of t dt, isn't it. So, this is the standard formula. So, the antiderivative is v for v prime. So, you substitute that and you get from the fundamental theorem. So, this would be v of 0 is given as 0 and you integrate from 0 to t e power minus t, so I am sorry, half e power minus t dt, and that will just be half times e power minus t is just minus e power minus t substituted between 0 and t. So, this is always confusing when the minus is there. You can pull the minus 1 minus out if you like, minus half, and then you will have just e power minus t substituted between 0 and t. This is a little bit cleaner and easier. Minus half e power minus t minus, if you put t equals 0, you just get 1. Okay, but there is a minus sign here, so it's half 1 minus e power minus t. So, that is your v of t. Okay, so that's the answer. It's very easy to find, and if you put t to infinity, this implies v of t tends to half, right. So, if t goes to infinity, e power minus t goes to 0, and v of t goes to half. Okay. So, that was a quick problem. It basically uses fundamental theorem of calculus and gets you to do an integration indirectly. Okay. So, this pretty much sums up the integration by parts and techniques of integration and all that, but I also want to show you one more thing, which we can stop it here, and I want to show you one more thing, which, so now there are a lot of numerical tools for integration. I want to show you one such numerical tool. Let me zoom a little bit so that you can see what I am typing. Okay, so this is a Python based tool, and there's lots of symbolic things possible. So, one of the most interesting symbolic tools you can have is something called SymPy. SymPy, in fact SymPy, let me just look at SymPy can do a lot of things for you. Let me just show you SymPy integration. Okay, so here is an example of SymPy integration. Let me zoom this a little bit so that you can read. So, I'm going to just type this out and show you also that it really works. So, SymPy is a Python module in which you can do integration and all those things. So, you have to call it first. Let me see if Colab has it. Okay, so there it is. Okay, so it has imported everything from SymPy, and you have to do this init printing, so to make it look decent, and I like to use the Unicode printing. Let me just see, init printing, use Unicode equals true. Let's do that. Okay, it has initted the printing, and then now you can call some integration. So, notice what it's doing. The first thing to do is to make a symbol which is x, symbol x. Okay, so this is just program, and after you run that, okay, it doesn't like symbol. I don't know what I made, what mistake I made. Oh, capital S. Okay, sorry about that. So, this would happen when you do that. Okay, so that has been executed here. So, you got a symbol x now. So, once you got a symbol x, you can do integration. So, notice what function is being used to integrate, right. So, let's throw in a little bit more of a complicated function. I mean, you can use any function you like. So, I'm going to do x times, so it's giving you some help and all that, you know. So, to do that, so you can come out of it, and then x multiplied by e power x, okay, comma x. So, we were doing this integration, right, using parts and all that. So, if you just do that, notice what it does, x minus 1 e power x, there you go. Okay. So, you had to do all these other complicated expressions, right. So, you remember x power 3, right. So, I was claiming that this will be something. Okay. So, x power for, I am sorry, there is a mistake in Python notation. X power is actually star star in Python. So, you can see. So, once you put x power 3 times e power x, notice the derivative there, right, x cube minus 3x square plus 6x minus 6 e power x. So, you can put any complicated function you like, right. So, you can put anything else you like here, any function, as long as in Python notation you have to put it. Once you put that, you will get the integration. So, today there are a lot of tools like this available for doing symbolic integration. Even definite integration you can do. The SymPy will have some definite integral formula, a lot of mathematical tools. So, I will urge you to get comfortable with SymPy and SciPy. Okay, both of these have a lot of numerical tools for integration, and also such kind of symbolic integration. SymPy has that. You can throw a lot of things, like for instance, we never saw this kind of function, right? 1 by x. How do you find integral of 1 by x? And there comes the answer. It turns out log of x is integral. We have not seen this function log so far, right? So you'll see that will work. You can throw in a lot of other functions you can do, like for instance, I don't know if sqrt works. It may complain. I think you'll do math.sqrt, right? Let's try some complicated looking function, x root of 1 minus x squared, right? So we don't know how to integrate it. Math is not defined. Okay, so does sqrt work in Python directly? Maybe not. Oh, it worked. Okay, notice, look at that. So it gave you integral for the square root of 1 minus x squared, which we don't know how to integrate it. Look at what it gives, x times square root of 1 minus x squared by 2 plus some a sign, which is a new function which we haven't seen before. So this is new functions that are showing up. So these kind of tools are very powerful. They can give you an integration for almost everything for which it exists. So in this day and age, it's unfortunately true that you don't really need to know to mug up all the methods of integration and all that, but it's good to know. It's good to do it correctly, right? So I would urge you to know some of the methods that are out there, but also learn a numerical Python tool, Python-based tool. It's free. This is completely free. You can learn this and be comfortable with it so that you can check your work. So in practice, when you do this, you really need to be comfortable with both the tool as well as the real, knowing how to do the integration. So more interesting is the applications of integration, where we will see how one can translate a problem, a real problem, into integration. That's more interesting for us to do. The actual integration itself, you can give away to a tool very easily. Okay, so let me conclude this section on integration with a few comments. Basically, integration is area under the curve, and the fundamental theorem of calculus gives you this wonderful view of integration as antiderivative. You go from f to f prime using derivative, and you can go back from f prime to f using integration. Okay, and there are various methods to find antiderivative. Easy cases are very easy. You can also have more complicated cases like substitution by parts. We have not seen functions of this type. How do you integrate these things? And I showed you a tool, and the Python tool can very quickly give you integration very easily. So this is also very important to learn and know. Okay, that concludes this lecture. Thank you very much.